Welcome to Lab 13, the final lab of the semester. And today we're going to be studying standing waves. If you've ever played a guitar and you pluck the string and look at it very carefully, you see it forms this like bowed shape. And the waves are traveling up and down from bridge to bridge and creating what's called a resonance condition. So when you tune the string just right, it'll produce a particular wave like that has a certain frequency which you've set. If you have a good ear, you'd set it to the right frequency so that you create resonance at a tone that you're interested in. And the waves on that string that are creating that shape are basically sinusoidal waves. So I have a spring here that I can stretch and demonstrate how that is. So actually I'm going to have Mr. Sylvester send the first pulse. He's going to go like this. He's going to take the wave and actually go like this. Just give it a nice little sharp flick like that. And what he's doing is he's creating a little bit of energy that he's sending down the spring like that. So go ahead, give that. All right, and a little bit bigger amplitude. And when it hits my hand, you can see when it hits over here, it's up like this, and then it goes down like that and heads backwards. So we'll do it one more time. Okay, and that's what happens when waves hit a wall, and this wall does not move. Then when the wave comes down here and pulls up on the wall by Newton's third law will pull down on the wave, and then the wave will return in the opposite direction. And that's what gives like when you look at your guitar string, gives it that bowed look. So now I'm going to send a nice rhythmic pulse, a nice rhythmic wave down the spring. And this is sinusoidal. And this is basically what your guitar string looks like when you pluck it. And if you've tuned the guitar just right, the frequency that I'm making this oscillate at would correspond to a note, a good note. But if it's out of tune, it's still going to do this, but it's going to do it at a different frequency. So what I can do here is I can change the tension in the spring so that when I do it now to get the pulse, I don't have to apply as much force. And it's oscillating much faster now that you can see that the wave is going up and down much faster. And if I put even more tension in the string and do that again, you can see it's oscillating much faster. And that's because the pulse is going down the string much faster because I'm putting more tension in the wire. And when I do that, the restoring force in the wire becomes greater. So it travels much faster down the spring. So now I can also take a particular tension in the spring and I can oscillate it and make it do what's called two antinodes, two bumps. So whenever you look at a standing wave, the bumps are called antinodes. And if I increase the frequency enough, so this is one bump right here. So that's one antinode. And now I'm going to up the frequency until I get resonance again. And so you got to get it just right, and there it is right there. So now there's two bumps, two antinodes. And right in between the two antinodes, you can see that the spring is not moving. That's called a node. And there's also two nodes at the opposite ends of the spring, where I'm holding it and where Mr. Sylvester is holding it. So I can up the frequency some more, and we'll go to like 3 or 4 standing waves. So there's 3 right there, okay? And you can see I have to jiggle it much faster. In fact, I have to jiggle it 3 times faster to create that pattern like that. So that's what we're going to be studying in the lab. Now the first experiment, we're just going to look at a particular amount of tension in the spring and count the number of antinodes we see as we increase the frequency. All right. So we're going to go through how we actually create with mathematics a standing wave in space. And up on the screen right here, I have the setup for the lab. So over here, this is called an oscillator. an oscillator here. It's hooked up to Pasco. This one has its own little frequency generator, but we're using Pasco to create the frequency in our oscillator. And down on the other end is the tension that we're creating in the string with the mass hanging on the end. And we're going to demonstrate that in the experimental part of the video. So the second video we'll be looking at that. But anyway, you can see right here that's called a node, and this is a node, and then there's two nodes on the ends. And we like to call this the 0th node. And then when we count the number of antinodes, it's the same as the number of nodes if we just call that first one 0. So this is 1 antinode, 2 antinodes, 3 antinodes. And if you go right here, this is 0, 1, 2, 3. And it makes the data collection a little bit simpler. All right. Now what's happening is there's a sine wave that's traveling down the string to the right, and when it hits the wall, it bounces back and travels the other way. Which means that those two waves at every single point in time must be adding together to produce this pattern that looks like, well, in fact, this case right here, these 2 points and nodes aren't moving at all. And then this point right here is like a mass on the end of a spring, and it's oscillating up and down, up and down, up and down like that. And less so as you move along. All right. So basically, this is just the two waves going down the string. So the first wave is this blue line right here, hits the wall, flips over, and then comes back and goes like that. Now if you look at the wall over here, see there's waves coming all the time. This guy right here plus that guy right there has to add up to 0, because that's a node. So that point never moves. Likewise, if you go to the other end, this wave right here and this wave would add up and would be 0 there. And then somewhere in the middle, if there's 2 bumps over here, somewhere in the middle there would be another node right there, which looks like that's the spot. You see, right there it would add up to 0. All right. Now the way we write a traveling wave. So a wave that travels through space that's sinusoidal is equal to how big the wave is, the amplitude, times sine of kx minus omega t. Now, in this function right here, sine can only see angles, but x is a distance down the x-axis, the way the wave is traveling. So we need to convert that into an angle, and that's what k is. And k is equal to 2 pi over lambda, the wavelength of the wave. Now I'm going to flip ahead to the next slide and show you what a wavelength looks like. So one wavelength that starts here, goes to its maximum amount, comes down to 0 again, and then goes to 0 again on this side. So it goes negative and positive, and that is one wavelength right there. Okay, so you see L up here. L is equal to two wavelengths right now. So that's one whole wavelength, and that's 2 whole wavelengths. And if you put that into the formula, okay, so if I put L equals 2 wavelengths or 1 wavelength, and then I multiply by 2 pi over lambda, then the wavelength's going to cancel, and right over here I'm going to have sine of like 2 pi, 1 pi, 3 pi, and so on, and you know that the sine of pi is equal to 0. Likewise over here, this is the same traveling wave, but now it's traveling back this way. It's traveling to the left in the negative x direction, and when you have the positive sign, you go with the opposite, and it actually is traveling opposite that sign. So this wave function right here is traveling to the right, and this wave is traveling to the left. And if you go, well, let's just pick a certain point in time. So this picture right here would be like at 5 seconds I took this picture, and then I just let this thing I just let this thing oscillate now, and it would just go up and down, up and down, up and down, up and down. But in space, with the combination of these two waves, the wave does not move. But as you know, it's got to be moving, because you see it's moving up and down. So the wave traveling this way plus the wave traveling that way is producing this net result, and that's called in mathematics, the principle of superposition. So we're going to add those two waves together, this wave plus this wave, and get the combined effect. And the combined effect is this function right here. So remember, both sine waves had an amplitude A. So when they're adding up together, we get double the amplitude. And then we have the sine of a position function right here, sine of x, and then over here we have omega t. So when x is equal to 1 wavelength, let's say, so right here, so when x equals 1 wavelength, we got wavelength divided by wavelength is 1, and the sine of 2 pi is 0. So right here, at this point right here, y is equal to 0. Now y is in the vertical direction, so y is up and down, x is across, and then time is on your watch. Time is on your watch. So this thing right here occurs because x is equal to half a wavelength, or 1 wavelength, or 3/2 of a wavelength, and so on. And the sine of that is always 0. Now, if you go to this place here, which is a quarter of a wavelength, and you put that in there, then you find out that this cosine omega t would make the wave go up and down, up and down, up and down, because a quarter of a wave would give us the value pi over 2, which is 90 degrees, and the sine of 90 is 1. So at these points right here, called the antinode, the points on the string are going up and down, up and down, up and down, through their full oscillation range, which is the amplitude, which would be twice the amplitude of one of those waves traveling down the string. So I hope that's making some good sense. All right, so now we can put a condition on making 0 down here. So if k, 2 pi over lambda, times L is equal to so many pi values, where pi is 1, 2, 3, 4, 5, then these points are going to be 0. Okay? So 1 pi, 2 pi, 3 pi, you plug that in here, and sine of pi, 4 pi, 5 pi is 0. And those are our antinodes. Those are our nodes. And if you want to count the number of antinodes, just call this guy 0 right here. And so you can see we have 1, 2, 3, 4 nodes, and likewise 4 antinodes. Because we're going to call that first one on the end 0. So every time you create a standing wave, you'll have so many wavelengths fitting into the distance L of the string, because L of the string never changes. All right. Anyway, here's a little GIF to demonstrate those waves. You can see the green wave is traveling to the right, the blue wave to the left, and you add those two up and you get the red wave, and you can see the amplitude is double, double what the green and blue waves have for an amplitude, and that just oscillates up and down, up and down, up and down. You can see there's a node right there, a node here, node here. So they put some spots right here, so you can see at any particular point, this green point is directly opposite the blue point, so it always adds up to 0. All right, now we're going to send you this PowerPoint so you have those pictures to look at when you're working on the lab and watching the videos. All right, so that's it right there. So now we're going to go to the experimental part of the experiment. And we're also going to do a little demonstration for you. We're going to actually create a standing wave on the string over here, and then we're going to hit it with a strobe so that you can see that if you produced a strobe that's turning a light on at the right rate, we can actually get the standing wave to freeze in space. So it'll be like, at the point it goes all the way up to the top, well, you won't see any of the points down below. You'll just see the point on the top. So it'll look like there's a piece of string that's suspended out in space, like a sine wave. All right, and we'll just go to the next